Hi everyone, this is Lab 4 Macroscopic Views of DC and RC Circuits, and I'm Jill Riley. As an introduction, we're trying to simulate ideal various circuit situations. So we predict behavior of circuits in series and parallel, which contain resistors and ammeters. We also measure conventional currents and potential differences of circuits using multimeters, and we examine ohmic resistors and capacitors for their behavior. To look at the applicable physics principles for this lab, we looked at energy conservation, current conservation, and Ohm's law. Energy conservation is the idea that loop rule, the sum of potential differences for a loop which is complete should equal 0. For current conservation, you're looking at nodes and you're saying that the current entering a node should be the same as the current exiting a node. And with Ohm's law, you're saying that the change in voltage should be equal to I times R, which is current times resistance. So our first part, charge conservation and energy conservation in series circuits. Before even setting up the system, we're asked to calculate the charge for I1 and I2. So I found I1 and I2 to be equal to one another because there's no split junctions and to be 0.02 amps. And yes, my predictions were right when I did end up simulating it in the PHYS simulator. And here you can see that when the volt battery was flipped backwards in the simulation, the ammeter then was reading a negative to negative 0.02. This is because the current was read backwards on the ammeter. So now we get into where we replace the ammeter with the voltmeter. So the potential difference that we're reading is 3 volts. And this is because the black wire that's attached to the battery has 3 volts and the red wire has 0 volts. So there's that change and that potential difference created of 3 volts at that station. So the ammeter itself is reading 0 amps because the circuit is open and the current is also just not flowing. Here you can see this main circuit that we created, and between AB, the 2 batteries, potential difference of 3, and there's also a change at the 2 resistors CD and EF. The CD resistor is smaller than the EF resistor, so you do see a smaller change in potential difference. Ultimately, due to the loop rule, these will all sum to be approximately 0 as it is a closed circuit. Here's an approximate graph of the potential difference relative to the negative end of the battery. And here again, you'll see the difference between A and B is 3 volts, between C and D is negative 0.96, and between E and F is at negative 2.04. And that's because it's that larger resistor. And there's that bigger jump. So then we're looking at attaching the voltmeter. We're altering the circuit. Why does the ammeter reading change? It doesn't change on the voltmeter because it has infinite resistance, so there's no current flowing through it. With the ammeter in parallel, you're seeing the ammeter changes to 0.06 amps instead of 0.02 because the current is now actually split between the ammeter and the 100 ohm resistor in parallel, and it's due to the node rule that it's now reading 0.06. So the ammeter has no resistance, and the 100 ohm resistor is pushing resistance, so the current tries to all go through that ammeter. And that means that the only resistor that's really being used is 47 ohm resistor, which is producing the 0.06 amp reading. So then looking at the resistance of each circuit element, R47 I found to be 47.95 ohms, R100 102.05 ohms, and R wire and R ammeter are both 0 ohms. This is because R wire has 0 volts of potential difference, and R ammeter, there's no resistance in the ammeter. Looking at charging and discharging a capacitor. So the capacitor will first start out where the light bulb is very bright, but then as time passes, it dims and eventually turns off because the current has stopped flowing because the capacitor is now fully charged. In the discharging simulation, you see the light again starts very bright in this bulb and it dims as time passes until the capacitor is entirely discharged and the current again stops flowing. This time, though, the current is moving the opposite direction when discharging the capacitor. For the 10 ohm bulb, the charge was approximately 10 seconds, discharge approximately 12 seconds. For the 20 ohm bulb, charge was approximately 20 seconds, and discharge was approximately 26 seconds. This is because the 20 ohm bulb has double the resistance, so it's approximately doubling the time to charge and discharge the capacitors in this simulation. Here, I'm determining RC value of the circuit with potential for each second measured and looking at that ln V over V naught. So I found the slope to be negative 0.1458. And to find RC, we do negative 1 over that value for a value of 6.85 for the RC. This does compare and agree to the RC value of the circuit in the CCK because that was approximately 6 seconds. So 6 to 6.85, a small difference there. Additional questions. So what if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about it? The overall current value would actually be marginally smaller because this real-life ammeter would have a small amount of resistance, unlike the ideal state where there's no resistance in the ammeter. And if we're doing this lab in real life and use a real battery to charge a real capacitor with no resistor in the circuit, it would not charge immediately as it would an ideal state of the lab without this resistor, because in real life, the components all have some resistance. So it would take a small amount of time to charge these. Thank you so much for following along, and I hope you have a great day.